Thank you, Jamil, for coming. And we have you here to share training and developing generative adversarial networks. I can't even pronounce it, so I'm really curious about how they work. GANS, in other words, and also how to make them fight. That's pretty cool. And thank you for sharing the link with us as well. I will give it to you and have you please introduce yourself further. Thank you. Just one switch over.
A couple of people, I can talk to everyone, and I can see if I can slow down or speed up depending on you guys' facial expressions. That'd be much appreciated. With that being said, let's begin. Welcome. My name is Jamil Gafur. If you want information about me, feel free to check the Google Meetup link. I don't think you're interested in me as much as about what I'm talking about, so we're just going to dive right in. Now, the presentation is called Introduction to Neural Networks and How to Make Them Fight. When you're with me, I am a very special individual in the sense my presentations are different from most college talks and stuff like that. It's very interactive, so your participation is key. The next thing is, don't wait till the end to ask a question. If you have a question, life is short, just ask it right now. And we'll try to figure it out. I'll give you an answer as soon as possible, or I'll have to think about it and get back to you. So remember, ask a question if it comes to you. Finally, all of the code has been compiled and already pushed to the GitLab repo, so I'll be using that. It has this presentation as well as the IPython notebooks for dense neural networks, convolutional neural networks, and GANs. So feel free to follow along there. Nice. So remember I said, it's interactive. Participation is key. So when we look at this, we have neural networks. The first word is neural. So when we say the word neural, what comes to your guys' mind? And I can't see the chat, but I'll have, now I can see it, haha.
Nerve?
Nice. Neutrons, no, the brain, great. So exactly. When we think of neural networks, we think mostly about nerves and the brains and how they interconnect. Essentially, neural networks are designed in a similar fashion to the human brain, where on the left-hand side, you can see not actual cells, a visual representation of cells in the human brain, where you have one neuron that's been activated for some reason, and it sends an electrical signal to another neuron. And the way that it's being sent down is via some electrical impulse. Well, it's not as strong as a car battery, but it also exists. So you have some kind of strong electrical impulse going between neurons. Similarly, when we look at neural networks, you have on the right-hand side a whole bunch of different input, X1, X2, and X3, and that's all being shoved into a given neuron. And from there, you can decide whether or not that neuron is on via some activation function, and it'll pass that information on. So now, I'm assuming everybody here has brains. That's a good thing. You should have at least one. If you have more than one, there's an issue, but that's another problem for another day. So we're going to see how fast your guys' neurons actually work. Can everybody in the chat say yes? Nice. So I'm going to put up a question. See how fast you guys can answer it. Are you ready? Here we go. 2 plus 2. Nice. A lot of people are full right off the bat. We're going to do another problem. Are you guys ready? Nice. Here we go. 26 times 4. Aha. 104. It took it not as fast as 4, but we're still getting there. Now, the last one. Ready? The integral of 0 to negative 1 of x to the 2x plus 1 over 2 times 4x plus 1 squared. Anyone? Someone? Ha! Great. So not a lot of people can figure this one out. You can try to solve it, and some of you might be able to. So that's how we're going to be moving forward. So essentially, we're looking at how fast you can recall information and recall previous experiences to answer a question. So this is mainly of what the activation function does. It compresses all of your previous information, and then it generates a scalar, which would be the electrical impulse in your brain, and moves it forward. Everybody here has seen 2 plus 2, 2 plus 2, the whole lives. But you guys haven't probably seen 26 times 48. But you know how to solve it. So it might take you some more time. The next one is that integral, that horrible integral. Well, it's not horrible. It did nothing wrong to me. But we'll just say it's a bad integral because it'll take a long time to solve. You might be able to solve it, but it'll take more time than adding or subtracting because you haven't done integrals your whole life. So if we go back to the brain now, we can see essentially how the electrical impulses, similar to the activation function, decides how much information moves forward to activate the neurons in your brain. Similarly, how it moves forward to activate the neurons in a neural network. So if we bring up a problem, 2 plus 2 is equal to 4, you guys have your neurons for that specific problem open. Now, why does nobody think about the ancient river valley civilizations when I say 2 plus 2 is 4? You guys know what ancient river valley civilizations are, but they have no need. The neurons in them are quiet. The neurons for ancient river valley civilizations are not on when I tell you 2 plus 2 is 4. So essentially, that's how you can visualize or understand how neurons work in a neural network. The ones pertaining to the input, 2 plus 2, are on, and the ones not pertaining to it, the Indus Valley River civilizations, are off. Now, when I'm talking about activation functions, there's a word in there, functions. Can anybody remember what a function does? Nice. Professor Sofianos, what does a function do?
Well, we pass values into it, it follows a process, and it shoots some magic stuff out.
Nice.
Am I close?
That's exactly it. It takes an input and it gives you an output. So there are different kind of activation functions. Two that we'll be going over is the sigmoid and the ReLU activation functions. The first one is the sigmoid. So if we think about that integral, you either didn't know it, so you'd be somewhere all the way down here, or you kind of know it, and you'll get some kind of value, and you might not know exactly the solution, but you can figure it out. So it'll asymptote at 1, and it'll say it'll mostly be on some of the times when that input comes. Now, correspondingly, if we look at ReLU, we can think about the activation of your neurons for 2 plus 2 is equal to 4. You don't know it? If you don't know how to add, you can never solve that problem. So you either don't know it and it's completely off, or you know it and you know it really fast and you can just get it. So in sigmoid, it asymptotes at 1, but ReLU, it's the maximum value. So it'll just go off immediately. While ReLU, it'll kind of be on for the most part, but not really. Great. So now we've essentially summed up how activation functions work in neural networks. So with that being said, there are different things in neural networks. We've talked about the activation function. So let's move on to the next thing, which are the rails. Neural networks are built up of multiple different rails. You have dense rails, convolutional, max pooling, flatten, and dropout. And by the time this talk is done, you guys should have a general understanding of what these rails do. So now the first rail we're going to look at is a dense rail. So a fully connected rail is essentially what a dense rail is. All of the nodes in one rail are connected to the nodes in the next rail. Now, some common terminology with building neural network models is as follows. You have the input rail at the top, and this is where your input would go in. And then you would have your output at the bottom, and that's essentially telling you your solution. Everything between the input and the output is considered the hidden rail. So in this case, we have an input rail with 10 nodes, so it can take 1 plus 2 plus 3 all the way up to 10. And then the output rail is one thing. So we can say, is the sum of numbers equal to something else? If it's equal, then we can say yes or we can say no. And that's an example of what this neural network is doing. It'll take a whole bunch of input, 10 numbers, and you can push it through and you can train it such that it'll answer the solution. Does the sum of these 10 numbers equal a different number? And since the output is one neuron, if it's on, that'll respond to yes. And if it's off, it'll respond to no. Great. So now we're going to go back and ask 2 questions and then do a coded example. Again, are you guys ready?
Hey, Jamil, in this model, each neuron is just a 0 or a 1. It's a binary.
Each neuron represents the function of its corresponding weights and vector of weights, the input associated that it came in with, and then an off bias.
Okay, so what would be contained in a single neuron? Like a numeric value, a list of numeric values?
It'll be a list of numerical values that came from all of the previous ones. So example, the neuron at the second left will contain 10 values
Okay.
from the inputs that it got.
So
now, those values might be 0.
Our inputs are numbers in this case?
Yeah.
Okay.
Nice.
There's another question in the chat from Daniel.
Numbers. This is all theoretical at the moment. So you can set it to be real numbers. You can set it to be imaginary numbers. It depends on how you train it. Like you can put in the letters of the alphabet or any kind of thing that you want. It depends on how you train it and then how you'd go about testing it. So this is just a blank canvas. It depends on how you put what you input into it. Nice. So now moving forward, I'm going to ask 2 questions and then we'll do a coded example. You ready? The first question, what is a dense neural network? That's right, it's a network of fully connected rails. The next thing is an activation function. I'll start you guys off. It is a function that A. Yep, an activation function determines if a neuron is active or not. Nice. So now with that being said, I'm going to stop sharing and then I'm going to move to the first coded example. Where we have in the Git repository, you have the first section, which is the dense layer example notebook. So the first thing we did, is I talked a little bit about, is we need to train the model. If we create a model, it's just there, it's a template, all randomly initialized. What makes a neural network good is its ability to learn and develop. So let's do that. In order to learn and develop now, we need to have data. We need to have information to send into the neural network. So we're going to import KLAS and a data set called MNIST. MNIST represents about 100,000 images, and each image is 28 pixels by 28, and it's all black and white, and each image is essentially a hand-drawn number. So what we're going to do first is we're going to load in the data, and we're breaking it up into 2 parts, the training data and the testing data. And each training and testing data has input and its corresponding output. So we have the X input for training and its output, the Y training. And correspondingly, we have the X testing information and the Y testing. Now, why do we want to have 2 separate things? Well, we want to have the training data so that we can train our neural network. And then we want to have our testing data so we can see if the training network can answer questions that it hasn't seen before. So like everybody's seen 2 plus 2, and we know that's correct. However, if I said 2 plus 27, how do you know you'd be correct? Well, we'd have to test it. So similarly, we have our training data and our testing data. So now moving forward, we have the number of features of, for our training set, 60,000 28 by 28 pixels. Now, just for fun, we're going to reduce the dimensionality such that it's 28 by 28, which is 784. And we're going to reshape it such that we have our 60,000 images, but instead of it being 28 by 28, we've essentially compressed that down. But this is all just data management with Python that you guys can look at later. The thing you're probably interested in is creating the model. So now we're going to have a basic model. It's called a sequential model, as previously shown, where just one layer with the next layer with the next layer, and it's all dense. We're starting off with, again, 28 by 28, which is 784 as the input. And then from there, we're going to have 32 nodes followed by 5 nodes. Finally, our output layer is going to have 10. These 10 nodes represents the numbers 0 to 9. So if the ninth node is on, that means the number we sent in should be a 9. If the fifth node is on, then the picture we sent in should be 5. So when we look at it, we have a pretty picture, which is fine. But we'd compile and we'd fit our model. So we're training our model on the training input and the training output. And we can't just shove everything in because I don't have that kind of space. I only have a 2 gigabyte GPU, so have to be very conservative with my memory. And essentially, we're going to push in 256 images at a time, 5 times, and we're going to print out some information. Now, when we do that, we can see that our accuracy is only 9%, 13%. So it's learning information, but not that good. So what happens if we just do, the basic thing of adding more, just throwing more neurons in? Hopefully it'll figure itself out. So say we move from 32, 5, and 10 to 512 a bunch of times. Does just adding more neurons help? Well, when we train all stuff, using, again, training input, training output, 256 for 10 epochs, we can see not so much. It's still doing the same, about 9. So now why is that? So let's go back to the presentation, share my screen. So let's look and take a break for a second. We said that it doesn't do really well. So we're going to pause there for a moment, and we're going to deviate a little bit, and we'll join back in later on. Can anybody explain to me what a duck is? How would you describe a duck to a computer? You'd say it has a beak, webbed feet. It has, it's usually brownish or yellow. Yeah. So if I were to show you a picture based on what we've said, this is a duck. This penguin is a duck. It has webbed feet and it has a beak nose and it's next to water. This kangaroo might have a beak, kinda. These ducks down here sure has beaks and it's yellow and it's a duck. So essentially, we have a whole bunch of single, when we look back, we had a whole bunch of single pixels. And now those single pixels were 28 by 28, and they had individual pixels. So when we looked at an individual pixel, we couldn't really understand what's going on. If I were to take a picture of a duck and change it into just a whole bunch of single pixels, one after the next, you wouldn't be able to identify it. So that's why they invented something called convolutions. Well, convolutions are a type of feature reduction, where it'll take a big image and it'll break it down into smaller pieces. So now you can have a convolutional layer which checks each individual section for, is this section a picture of webbed feet? Does it also have yellow? Is it next to water? Is it fit these different constraints? And now the convolutional layer can do some matching and say, 7 out of these 10 things show up for a duck. Therefore, I'm 70% sure it's a duck. However, if I just send in a whole bunch of pixels, it wouldn't be able to put 2 and 2 together. So convolutional layers preserve the relationship between pixels, and it can find features within an image that would be interesting for us to pay attention to when we're looking at new models. So we can go here to this site and say if we wanted to look at the number 3, we can turn off all of the different rails except the first convolutional rail. And we can see in this instant on the left-hand side, it's noticing all of the bottom streaks, all of the straight lines on the bottom of the 3. The one on the right are all of the top lines of the 3. The one over here is finding all of the features on the bottom right-hand corner of the curve of the 3. So now we can start identifying unique features of an input image so we can pattern match them later on. So this is an example of a convolutional rail. The next thing we can do for feature reduction is we can do max pooling. And max pooling essentially says, I don't care too much about what's going on, except for the most important thing. So in this case, we pick a small subsection, and the max value is being stored. So if we go back to our picture of a duck, I don't really care too much about the water over here, but I do care about the tail. So the tail would be the most active pixel. So then we'll save that pixel. And then that's how we can reduce the feature dimension. So we can get rid of all of the water or all of the different things we're not really interested in. So now we're going to take another pause and go on to the second programming example and then move forward. So here, remember, we took a pause for the first one, and now we're coming on to this one. So we're going to see how we can do better by using convolutional rails and max pooling. So we have the same loading in of the data where we transformed it. And now here, we're not going to add too much stuff. We previously had for our first rail, where was it? 32, 5, and 10. 3 rails. The first one had 32, the next had 5, the last had 10. We're going to keep the same format. We're going to have 32. We're going to do max pooling. And then from there, we're going to have another convolution, another max pooling, and we're going to flatten it out. And this is essentially the same as what we were doing before, where we had all of the individual pixels. That's what the flatten does. It takes it away and flattens it down into one dimension. And then we have our normal dense neural network. And instead of using the linear activation function, we're using ReRU. So it's a couple of changes. And with that, when we train our model on the same X training, Y training, with a little bit bigger batch size, we can see that we're moving up to 70% accuracy. And I'll let you know now, and feel free to try this later on. If you were to train this for 20 epochs or even 30, you'll be hitting about 99% accuracy. Great. I'm going to take a quick pause for a moment because I threw a lot at you guys. Does anybody have any questions? Pause for dramatic effect.
What do you mean accurate?
What do I mean?
You like define accuracy. I mean, I'm guessing that means how off it is from the expected output.
Yep. So the accuracy is determined not by the training data, but by the testing data. So you send in the testing data, and you know what the correct answer is, and you know what the predicted answer is. And the accuracy is just the difference between the two, is the division of the two. Does that help out, Alex?
Yeah, I just can't. You said our training data were
so we have
28 by 28 images.
Yep.
And you made 60,000 of those.
Yeah.
You need
and
10,000.
Solution to them all.
You know the solution to each one.
Yes.
Okay.
So accuracy is how many times we got it correct.
Oh, okay. Sure.
Nice. Any other questions, comments, concerns, and/or threats? Nice. So let's move on to the part you guys have been interested in. Oh, before I forget, we have to talk a little bit about overfitting and underfitting. And thank you, Alex, for the segue with the accuracy. So we have our training data, we have our X and our Y coordinates, which can be represented by these blue dots. If we underfit, we're not doing an accurate representation of how best to decide which is which. If we overfit, that means our training data, 100% of the time, we'll get it extremely correct. But the second we introduce new information, we're just going to assume incorrectly because we've only memorized it. Then we have a good fit, which it's not 100% correct, but it's correct most of the time. You guys can think of this as taking a test. If you memorize the solution and the question, when somebody gives you something slightly different, you won't know what to do because you've only memorized one instance of the question and the solution. So that would be considered overfitting when you memorize a solution to a specific problem. A good fit would be learning the underlying material and the foundation of the problem. And then, underfitting will be, the professor said it once, I can wing it. That's a good example of how you guys can think about the difference between underfitting, overfitting, and a good fit. Now, there were two other rails that I talked about, flatten and dropout. Well, essentially, let me pull up, if for flatten, if you have a matrix that's 2 by 2 with 1, 2, 3, and 4, when you apply the flatten to it, you get, basically you're compressing all of the dimensions into one, so it'll just be 1, 2, 3, 4. Which is what we did for the first test, where we essentially just shoved everything in the 728 pixels into the neural network. The next thing we were doing is dropout. So a dropout rail essentially says, in order to avoid overfitting, we're going to sometimes ignore a couple of neurons. And these neurons will, be off for sometimes, other times they'll be on. So that way you can understand the underlying foundation of the knowledge without being too fit on what's going on. So we can go back to, let's clear out this drawing. If we go back here, you don't want to hold on to every individual thing. For example, this region here is highly overfit because it's hitting every particle. So you'd implement dropout to essentially smooth that line out, so it won't overfit and have every individual particle being recognized. Great. So now, congratulations. You now have a general understanding of how to build neural networks. Ooh, great. Now here's the part we're interested in. How to make neural networks fight each other. And now this is a whole area of research that couldn't be covered in an hour. So I'm going to do more of a hand-waving understanding of it. And then we'll go into the coding if we have time. But again, if we don't have time, the code is made available to you guys with the environment set up and everything.
There is a question in the chat.
Can we partially train on images, like showing lots of tails on the left half, and presumably it would be good at identifying tails in that left half? Yes, that is something that you can do. And that is an area of research that it's not for identifying, but it's actually for attacking neural networks. Well, there's been cases for self-driving cars where people would put a yellow square on stop signs, and then neural networks would say to stop when you see either a yellow square or a stop sign. And then from then on, people would be able to break these neural networks, these self-driving cars, by essentially just having a yellow square on the person and forcing the cars to stop. So similarly, if you train on the left side with tails, you'd be able to identify that. Good question. Nice. So moving forward now, getting back to generative adversarial neural networks, it's actually, in order to fight, you need to have two things. You can fight with yourself, but that's not as fun as fighting with someone else, in my opinion. So essentially, what a generative adversarial network is, it can be comprised of two neural networks. The first neural network is a discriminator. So that's essentially saying, is the picture that I'm given part of the data set, or is it not part of the data set? The next neural network essentially generates images that says, I want to forge this image and I want it to pass the forgery. So you can think of it as a cop going with a forger or anything like that. So the generator generates fake images and the discriminator says whether or not it's fake. So let's look at the discriminator for a moment. The discriminator maps a set of common features to a set of specific labels. So it tries to take an X and figure out what the Y is. And the next thing is that it learns boundaries for each features and decides whether or not to classify it. So if I am the discriminator, and essentially if I'm a cop, I want to learn how best to represent my data. So we're going to have an example. Professor Sofianos is going to be a criminal, and she's going to try to forge a dollar bill. And I'm a police officer, and I'm going to see if she has a forgery or not. So as the discriminator, I know what a dollar bill looks like, and I'm going to study what dollar bills look like and the codes represented with them and the shiny filament on them and all of that fun stuff. And Professor Sofianos is going to try, there we go. Professor Sofianos is going to try to trick me. So that's essentially what the generator does. It tries to trick me with what a dollar bill is. So Professor Sofianos, she starts off with that nice drawing of a smiley face, and I say no. And then she's going to change that picture of a smiley face to be maybe Abraham Lincoln. So she's going to learn essentially why I said no. And then I'm going to say no again because it's not on a Post-it note. And then she's going to get a real dollar bill. And see how she gets better and better? That's essentially what GAN does. You have some random noise that she initially started off with, and then it generates the little Post-it that she decided, and I say it's fake. And then she'll make updates, and then I'll say, no, it's fake. And she'll keep making updates until I say, you know, I'm like 80% sure that that's not a dollar bill. And then I'll be 70% sure, and then I'll be 60% sure. And that's how we're making them fight each other. Because I know what a dollar bill looks like. I have my training set, and she's just generating random images. So that's essentially, see, look how that, you could go to a deli and pass that off 100%. So now what we're going to do, instead of doing dollar bills, because that's illegal, forging money is illegal, kids, we're going to go and try to draw a picture of an apple. Do we have time? We have 8 minutes. Think we can get it done in time? So we have now our imports. Well, it's a lot of imports, but it's nothing new. We have our dropout, we have our flatten, our activation, our dense, our convolution. And now what we can do is you can download the data here, but we're essentially going to load in our data. And from there, we can see its shape. We have 144,722 pictures of a drawing of an apple. What's an example of an apple? This is a picture of an apple. So I am the police officer, and I have 744,000 images of an apple. Differently drawn, but for the most part, it's an apple. We can recognize it as one. So now let's build myself the discriminator. Well, we take our input, which is the 28 by 28, and then we have our normal classifier, which we talked about before, which is some convolutional neural net, convolutional layers, a flattened layer. To prevent overfitting, I tossed in a dropout layer just for fun, but feel free to play around with how you'd want to develop this yourself. And then for the last layer, it's going to be 1, which is, yes, it's an apple. No, it's not an apple. Now let's build the discriminator. So we're going to build the forger. So now our forger, it's going to take in 7 by 7 by 64, which essentially, I don't know why I put that though. It's the input dimension. The same as what we've had for our generator, the image width and the image height. From there, you know, we're going to normalize everything to be between 0 and 1 because we're generating a lot of images now. So I don't want to generate 255 by 255 and have exponential growth. So I'm basically normalizing it so it'll be easier to handle. From there, I do some fancy programming stuff. I only have 5 minutes, so I'm going to hand wave this a little bit. And then for the output rail, it's going to be essentially 1, where it'll be the output of the image that we've made. So now we have our generator and we have our discriminator. Let's put them together. We have now our adversarial model, which is just a normal model with a generator and a discriminator. And we're going to name it adversarial. Have I lost anybody so far? I'm going to take that as a yes. But nobody's going to say anything. So I'm going to keep going until somebody says something. So now what we're going to do is I have 1 GPU. I don't have a fancy GPU. I only have 1. So I made this little function, which is make trainable. Since my code runs on a GPU for each neural network, I'm essentially going to say either the generator is active or the discriminator is active. If I had 2 GPUs, I wouldn't need that, but I'm a grad student. I don't have 2 GPU kind of money. So now we're going to train our model and see how well we're going to do. So we're going to get the real image, which is essentially the data, and we're going to have a fake image, which again is some random noise. From there, essentially what we're going to do is we're going to train our adversarial model and train our discriminator. And then one's going to train, make some output, send it to the discriminator. The discriminator saying, this is 99% a no, this is 89% a no, and it's going to find out why one was 89 and one is 99, and it's going to make some updates, and it's going to try to trick the discriminator. And here I put in a little thing that essentially says, at every 10th epoch, we're going to print out the loss, and we're going to print out the generated image. So when we start off at 10 iterations, can anybody tell me if they think this looks like an apple? Feel free to put that in the chat. Nice. This does not look like an apple. But, you know, it's like, oh, the discriminator says this is, I'm 9% sure this is a picture of an apple. However, on the other hand, we have not so much. So as we keep training and we keep trying to figure out how to trick the discriminator, we can move down. Oop. 1 second, so I pushed the wrong button there. I should have made this a GIF, G Wilkles. There we go. So as we move down, we can see the generator starting to learn specific features that'll make the discriminator more likely to say it's an apple. So we can see a curve starting to form for where the apple should be. Now we're getting some dark spaces. And as we keep iterating through, we can see, okay, we're starting to generate some kind of circle for the base of the apple. And we keep iterating and we keep iterating. And the generator is going to try as many different permutations possible to generate new images to decrease the accuracy of the discriminator. And now see, like, this is doing pretty well. It's not 100% like an apple, but it's starting to take on that form. So this generator is fighting with the discriminator to generate better images. And the discriminator is fighting with the generator to make sure that it's not generating better images. And we can see as it's moving forward, we get to be more and more better pictures of an apple until we hit, say, iteration, let's go, about 1500, we're starting to see a better apple. Now this took me about 15 minutes to run. Imagine if you had 2 GPUs. Imagine that problem was more not an apple. What happens if we were trying to actually generate an image of the dollar bill? This is a whole new research area where you can generate deep fakes, where you can generate images of things that don't exist. If you're interested in deep fakes, feel free to email me and I can talk to you more about that. But I think I was able to basically get it on the skin because we're out of time. If anybody has any questions, feel free to message me privately or email me. You have my contact information on the Google Development website. Thank you for your time.
Thank you, Jamil. I'm gonna pause the recording for a second while we switch gears.